So in the previous session, we were discussing about the luminescence, and under luminescence, we were discussing about the fluorescence and phosphorescence. Now, let us see what are the how the electronic changes lead to the luminescence. What are the process, physical or chemical process happening during the photochemical process? In order to understand that, we need to have an idea about the electronic states of the molecule, how the electrons will be arranged. Each electron in a molecule carries a spin angular momentum with a spin quantum number s is equal to half. It has two possible orientations. One is minus half, the other one is plus half. Electrons, generally we take two electrons together in an orbital, can have two different orientations. One is what we call singlet state, electronic state of a molecule in which all the electrons are spin paired. Total spin quantum number is equal to 0. There is no unpaired electron. So S is equal to 0 because inside a molecule, if there is no unpaired electron, so one electron will be like this and the other electron will be like this, so that the one of the electron is having a plus half spin, the other one is having a minus half spin, so both will get cancelled. So the total spin quantum number will be equal to 0, and the spin angular momentum we generally used to express in terms of spin multiplicity, that is given by the equation 2s plus 1. So here s is equal to 0 and 2s plus 1 is equal to 1. So the spin multiplicity of singlet state is equal to 1. The other possibility is triplet state. Here two electrons are not spin paired, they are in parallel condition. So electronic state of a molecule in which two electrons spins are parallel may not be in same orbital, it will not be in same orbital, they are in two different orbital, but the electrons are not in paired condition. So when they are not in paired condition, the spin of one electron and the spin of the other electron will get added. So if it is minus half, the other one also will be minus half. If one is plus half, the other one also will be plus half. So plus half and plus half could be added, minus half and minus half could be added. So the total spin will be equal to 1. And when you apply the spin multiplicity equation, that is 2s plus 1 will be equal to 2 into 1 plus 1, that is equal to 3. An electronic transition. So I am talking about the electronic state to stress on this point. The point is, an electronic transition is more probable if there is no change in spin multiplicity. So S could be 0, for its excited state could be, if the energy is absorbed with the same multiplicity, then it could be S1, could be S2, it could be S3, like that. So electronic transitions are allowed if there is no change in spin multiplicity. So from here to here is okay, from here to here is okay, from here to here is okay. Whereas here, triplet state, for that the spin multiplicity will be 3. So T1, T2, like that you can write. So you already have a zero state, singlet state. From here to here transition is not allowed because here the multiplicity is 1. Here for triplet state the multiplicity is 3. So from 1 to 3 spin multiplicity is not possible. Whereas 1 to 1 is possible, 3 to 3 is possible. So T1 to T2 is possible. This is not possible. This is what the rule says. The electronic transition is more probable if there is no change in spin multiplicity. Mechanism of this fluorescence and phosphorescence. So for that, we have to recall what we have discussed in the previous state. A singlet ground state could be represented like this. Here two electrons are in paired condition. Singlet excited state, where a pair of electrons with opposite spin but each in different orbital. So both are having same spin. Singleted excited state, a pair of electron with opposite spin but in different orbital, having different spin. And this is what we call singlet state, but it is in a different orbital. The other one is a triplet excited state, not a triplet ground state. Triplet ground state is not possible. Pair of electrons with parallel spin in different orbitals. It's like a small amount of energy is absorbed. That energy is sufficient to inverse the spin of a molecule, of an electron of a molecule which was there in the singlet state. So these three are possible. And what is fluorescence, if you ask? If the de-excitation of electrons happens from S1 to S0 or S2 to S1 like that, you may expect fluorescence. Whereas if it is from T1 to S0 or S1 like that, there is a spin inversion, because this has to make into this format. So this inversion is forbidden. So it's a slow process. That's why in phosphorescence the radiation is emitted for little long time. So in the excited species can return to the ground state by losing all of its excess energy by any one of the paths shown in Jablonski diagram. Suppose an electron is a molecule in an electron is absorbed certain radiation as a part of photochemical process. So right now it is in the excited state. So when an electron is in the excited state, what are all the possibilities that will make the electrons to lose the energy and will make the electron back to its ground state? So what are all the possibilities? In order to explain this possibilities only, there is a special diagram, we call it as Jablonski diagram. So let's see what is that. So this is what the representation of a Jablonski diagram. You have to draw this in a paper and you have to understand. So photochemistry deals with the electronic transition. So the electron will absorb energy, will get excited to next energy level. Photochemistry deals with the spin, more or less. So here you could see many lines. So each line represents vibrational energy. Vibrational energy means like if this is S0 at this stage, vibration will be more than this. So this line represent vibration. Time being, we are not discussing about this vibration and rotation. We only discuss about the electronic energy level. So what we have is S0, S1, S2 and T1. You have to draw this. You have to represent energy left hand side. ABS means absorption. Vertical line shows absorption. Here all the lines, that is blue, green, red and the vertical lines, solid line represent absorption, radiative transition. That means radiation is absorbed or emitted. So absorption, fluorescence Fluorescence is written as in the green color. I have told you it's a allowed transition. There will not be any change in spin multiplicity. So the green line represent allowed transition. So energy will be emitted. So fluorescence is a radiative emission. So radiation will be emitted during the transition. And the second one is phosphorescence. Phosphorescence is also a radiative transition because it is from T1 to S0. It's a slow process because as per the selection rule of electronic transition, it is forbidden because spin multiplicity is different. The other one is vibrational relaxation. Vibrational relaxation means, you could see here, this is dotted line. So here what is happening is, it is in the singlet state, ground state, but higher in vibrational energy. So it can, relaxation means the vibration could be reduced by emitting little energy, but it not be in the form of radiation. Means the vibration will be transferred to another molecules. Then IC, internal conversion. So internal conversion means an electron which is in S1 can come to S0 without emitting any radiation. That is called internal conversion. The other one is ISC, intersystem crossing. In a transition, it's not a radiative transition. It's from singlet state to triplet state without absorbing or emitting energy. For that, the singlet triplet energy gap should be very low. It is possible in ketones. Best example is benzophenone. In case of benzophenone, the gap between the triplet and singlet state is very small. So intersystem crossing is possible. Explain the give a knot on Jablonski diagram, or explain the various process that is possible to de-excite an electron from after absorption of a photon or radiation. If they ask like that, you have to give the diagram of Jablonski diagram, and you have to give a small writing about each process. So radiative process means they involve a vertical change in the energy, which is an increase when the photon is absorbed and which is a decrease when the photon is emitted. So here the vertical lines means the solid line which is directing upward or downward is what we call vertical line. All those represents radiative transition. Absorption is radiative transition, fluorescence is radiative transition, and phosphorescence is radiative transition. Actually, this dotted lines, if you refer the other textbook, it will be written like this, wavy like, zigzag way. Those lines represents non-radiative transition. Fluorescence. So we are talking about the radiative transitions. The first one is fluorescence. Ground and excited state have the same multiplicity, usually S1 to S0, and the nanosecond time scale. NS means nanosecond time scale. It is spin allowed transition. That's why immediately that emits the radiation. Actually, this fluorescence, the term is coming from fluorite mineral. And when the fluorite mineral is exposed to ultraviolet radiation, it emits some color, that's why. And phosphorescence, next radiative transition is phosphorescence. Here, ground and excited state have different multiplicity, that is T1 to S0, from hundreds of nanosecond to seconds. So it will give radiation out quite a long time. The reason is it is spin forbidden transition. And the non-radiative transitions are, they involve the internal reorganization of the energy of the molecule, a conversion from one state to another at a constant energy. Horizontal transitions. So non-radiative transitions are represented in the diagram horizontally, and also it is something like dotted or the wavy way. First one is internal conversion between the electronic states of the same spin multiplicity. So internal conversion means S0 to S1 or T1 to T2, T1 to T3, like that. There is no spin multiplicity change. The other one is intersystem crossing. We have already discussed about intersystem crossing, the conversion between the electronic states of different spin multiplicity. Vibrational relaxation, the other one, you could see VR, it's written over here. The energy of the molecule is eventually degraded as a heat to the surrounding in solution. This excess of energy is rapidly removed by the collision with solvent molecules. So this is what about the Jablonski diagram. There is a rule related to luminescence emission. Luminescence emission we have already discussed. Luminescence emission is observed from the lowest excited state of any given multiplicity, for example S1 or T1. Right? State means S1, T1, like that. So photosensitization, I have already told that the heat could be the energy could be transferred to another molecule. So when the molecule is getting de-excited, a possibility is, without giving any radiation, the molecule could transfer the energy to another molecule. Best example is photosensitization. In photosensitization, actually a molecule, it is in triplet state, it can transfer its energy to another molecule. Photosensitized reaction, an electronically excited molecule can transfer its energy to a second species, which then undergoes a photochemical process even though it was not itself directly excited. Mercury is the best example. The reactions are like this. Mercury absorbs a light and it is getting excited, and from the excited state it transfers energy to hydrogen. Chlorophyll is a photosensitizer. The reactions are like this. This is very important reaction. That is what we call photosynthesis.